There is a particle. Right now, somewhere in the space between the atoms of your hand, there are particles that have no definite position. Not because we don't know where they are, not because our instruments aren't precise enough, but because, according to some of the most carefully tested theories in the history of science, they genuinely do not have a position until something measures them. They exist as a cloud of possibilities, a smear of probabilities spread across space. Not here or there, but everywhere and nowhere simultaneously. Every possible position the particle could occupy exists in a kind of suspended potential, a superposition of all outcomes at once. And then something happens, something observes, something measures, and the cloud collapses. The particle chooses, or appears to choose, or is forced to choose, or, and this is where the question gets strange, the act of observation and the act of choosing are somehow the same thing. That is not a philosophical position. That is a description of what the mathematics of quantum mechanics says happens every time a measurement is made. The precise interpretation of why it happens, what it means, what is really going on beneath the mathematics, is one of the most fiercely contested questions in all of physics. Scientists have been arguing about it for 100 years. They are still arguing about it today. But here is what makes the argument so unsettling. The question refuses to go away. Every attempt to explain away the role of observation, every interpretation that tries to restore a simple, observer-independent reality, runs into something the mathematics keeps insisting on. The act of measurement matters. The act of looking changes things. And in some interpretations, not all, not settled, not certain, that dependence on observation goes all the way down to the question of whether anything is real when nobody is looking. This is where we need to be careful, because the claim that reality doesn't exist until observed is one of the most misrepresented ideas in all of popular science. It gets pulled out of context, stripped of its uncertainty, and stated as fact by people who have simplified past the point of honesty. The truth is more complicated and more interesting than the simplified version. And the truth is that nobody, not one physicist alive today, fully understands what quantum mechanics is telling us about the nature of reality. What they do know is this: the question is real. The experiments are real. The strangeness is real. And the implications, if certain interpretations are correct, are the most profound and most unsettling in the history of human thought. Let's follow them. The experiment that started this entire conversation happened in the early 20th century and has never stopped producing results that demand explanation. The double slit experiment. You fire particles, electrons, photons, even large molecules, at a barrier with two narrow slits cut into it. On the other side, you place a detector screen. If particles behaved like tiny bullets, you would expect two bands of impact on the screen, one behind each slit. Instead, you get something else entirely: an interference pattern. Dozens of alternating bands of impact spread across the screen in exactly the pattern you would expect if each particle was behaving like a wave, passing through both slits simultaneously, interfering with itself, arriving at the screen as the result of that interference. Each particle, individually, one at a time, passing through both slits at once. And then you decide to find out which slit the particle actually went through. You place a detector at one of the slits to measure which path the particle takes, and the interference pattern disappears. The moment you acquire the information about which path, the moment a measurement is made, the particle stops behaving like a wave passing through both slits and starts behaving like a particle passing through one. The act of measuring the path destroys the interference. Remove the detector. The interference pattern returns. This has been confirmed thousands of times in laboratories across the world with increasing precision and increasing variety of particles. It is not controversial as an experimental result. What is controversial, what physicists have never agreed on, is what it means. Here is where the interpretations diverge, and where you need to hold the uncertainty carefully, rather than reaching for a clean answer that the science does not actually provide. The Copenhagen interpretation, the oldest and still most widely taught, says that the wave function, the mathematical object describing all possible states of a particle, is real in some sense before measurement and collapses to a definite state upon measurement. It is deliberately agnostic about what causes the collapse. It says calculate the probabilities, make the prediction, compare with experiment, and stop asking what is really happening between measurements. It works. It is extraordinarily accurate, and it leaves the interpretation entirely open. The many worlds interpretation says the wave function never collapses. Every possible outcome of every measurement actually occurs in branching parallel realities that never interact with each other. In this picture, reality is always definite. It is just vastly larger than we can observe. No observation is required to make reality real, because every version of reality exists somewhere. But the cost of this interpretation is a universe of incomprehensible size and complexity that we can never access or verify. There are others: pilot wave theory, relational quantum mechanics, QBism. Each one attempts to resolve the measurement problem differently. Each one preserves something at the cost of something else, and none of them has been definitively confirmed over the others because, and this is the honest position, the experiments so far cannot distinguish between them. What the experiments can confirm is the strangeness itself, the dependence on measurement, the disappearance of the interference pattern when information is acquired, the fact that the act of looking changes what is found. And this is where the question that drives this entire video arrives. Not what does quantum mechanics say about particles, but what does it say about the universe itself? If individual particles behave strangely in the presence of observation, if the act of measurement shapes outcomes at the smallest scales of reality, then what does observation mean at the largest scale? Does the universe as a whole have a definite state? And if something like observation is required for definiteness at the quantum level, what was observing the universe before observers existed? This is the question physicist John Wheeler spent decades trying to answer. Wheeler was not a fringe thinker. He was one of the most important physicists of the 20th century. He worked with Einstein. He coined the term black hole. He developed quantum foam. And in the final decades of his life, he became increasingly convinced that the relationship between observers and reality was not incidental but fundamental. That the universe was not a machine running independently of the minds inside it, but what he called a participatory universe. A cosmos that required observation to bring it into definite existence. Wheeler's most provocative thought experiment was what he called the delayed choice experiment, a variation of the double slit experiment in which the decision about whether to measure which path a particle takes is made after the particle has already passed through the slits. The result, confirmed experimentally, is that the particle's past behavior appears to change retroactively based on a measurement decision made in its future. The particle behaves as though it always took a definite path or always behaved as a wave, depending on what is decided after it has already done whatever it did. Wheeler extended this cosmologically. Using the gravitational lensing of light from distant quasars around intervening galaxies, he proposed that we could, in principle, make a delayed choice measurement on photons that had been traveling for billions of years, photons that left their source long before Earth existed, and the measurement we make now, in the present, would determine what those photons were doing for the billions of years before we existed to observe them. Wheeler did not claim this proved the universe needed observers. He was more careful than that. but he believed it suggested something profound about the relationship between observation and reality that physics had not yet fully grappled with. That observation was not just something that happened inside the universe, that it might be something the universe was doing through us. Now, here's the section that most discussions of this topic avoid, because it is where the question stops being abstract and becomes personally uncomfortable. What counts as an observer? If observation plays some role in the behavior of quantum systems, if measurement matters in the way the experiments suggest it does, then the definition of what constitutes a measurement matters enormously, and physics does not have a clean answer. Does a camera count as an observer? A camera records information about a particle's position. It acquires the data that constitutes a measurement. In every experiment ever run, a camera detecting which slit a particle passes through destroys the interference pattern just as effectively as a human eye does. So in the operational sense, in the sense that matters for the experiment, yes, a camera observes. Does that mean consciousness is not required? Perhaps. The Copenhagen interpretation never required consciousness specifically. It required measurement, the acquisition of information, without specifying what kind of system had to do the acquiring. But then the question moves. If any physical system that acquires information counts as an observer, then the universe is full of observers. Every particle interaction involves information exchange. Every collision, every absorption, every emission, all of it constitutes a kind of measurement in the broadest sense. In this picture, the universe is observing itself constantly at every scale, and the question of whether reality requires observers dissolves into the observation that everything is already observing everything else. And yet the question refuses to dissolve cleanly. Because some interpretations, not all, but some, do require something more than just information exchange. Some versions of the measurement problem suggest that conscious awareness plays a specific and irreplaceable role in the collapse of the wave function. The physicist Eugene Wigner proposed what is now called Wigner's friend, a thought experiment in which a conscious observer inside a sealed laboratory makes a measurement, and the question of whether that measurement has actually collapsed the wave function depends on whether anyone outside the laboratory is aware of the result. In Wigner's formulation, consciousness was not just a convenient shorthand for measurement. It was the thing that made measurement real. This interpretation is not mainstream. Most physicists find it uncomfortable and try to avoid it. But it has never been definitively ruled out. And recent experiments, variations of the Wigner's friend scenario run at the quantum scale, have produced results that some physicists interpret as evidence that different observers can have genuinely incompatible accounts of the same quantum event, that the facts themselves may depend on who is observing. That implication is so strange, so resistant to easy dismissal, that it has produced serious academic papers in the last 5 years from physicists who are not trying to be provocative. They are trying to understand what the experiments are saying, and what the experiments appear to be saying is that the role of observation in quantum mechanics is deeper and stranger than the standard textbook account suggests. So where does that leave us? We have particles that behave differently when observed than when not observed. We have experiments that suggest the past behavior of light can be influenced by measurements made in the present. We have serious physicists who believe consciousness plays a fundamental role in bringing reality into definite existence, and equally serious physicists who believe it plays no role at all. We have a question that has been unresolved for a century, despite the most sustained and precise experimental effort in the history of science. And we have the universe, 13.8 billion years old, containing hundreds of billions of galaxies, producing, somewhere in its history, the first observer, the first system capable of acquiring information about its surroundings in whatever sense is required for quantum collapse, the first eye that opened on a reality that, in some interpretations, may not have been fully real before the opening. Before that first moment of observation, before the first measurement was ever made anywhere in the cosmos, what was the universe? Was it a vast superposition of every possible configuration of matter and energy, waiting for something to observe it into definiteness? Was it already real in some deeper sense that doesn't require observation? Was it running on rules we don't yet understand that produced both observation and reality simultaneously? Nobody knows. The mathematics doesn't tell us. The experiments don't reach back that far. And the honest position, the one Cosmora is always going to take over false certainty, is that we are dealing with a question whose answer has genuine consequences for everything, and whose resolution has not yet arrived. Which brings us to the end. Not the end of the video. The end of everything. 1 trillion years from now. A number so large it makes the current age of the universe look like an eye blink. The last star will exhaust its fuel and go dark. The stellar era of the universe will be over. What follows is a period of almost incomprehensible emptiness. A universe of cold remnants, slowly evaporating black holes, and the gradual dissolution of all structure into the thermal noise of maximum entropy. In that darkness, somewhere, the last conscious mind will exist. The last observer. The last system in the universe capable of awareness, measurement, information acquisition, whatever the precise definition of observation turns out to require. It will exist in conditions we cannot fully imagine, in a universe so cold and so dark and so empty that the concept of life as we understand it will have long since become impossible. And then it will cease. The last observer will close its eyes for the final time. The last measurement will be made. The last wave function will collapse. And then, in every universe where observation matters, there will be nothing left to observe. What happens then? Does the universe collapse back into superposition? Does the definiteness that observation has been maintaining, if it has been maintaining it, dissolve? Does reality become a vast quantum fog of every possible state simultaneously, with no observer left to select any particular one? Or does nothing change? Does the universe continue exactly as it was? Stars gone, black holes evaporating, entropy rising, indifferent to the absence of the minds that once measured it? Does reality turn out not to need observers at all, and the entire question we have been following dissolve into a beautiful but ultimately empty philosophical puzzle? If you are the kind of person who finds the questions that have no clean resolution more honest than the ones that do, if the suspended uncertainty at the edge of human knowledge is where you feel most awake, then Cosmora is where you belong. Subscribe and stay. There are questions ahead that go even deeper than this one. But before we close, here is the thought that belongs to you now. Perhaps reality doesn't need observers at all. Perhaps observers are simply another part of reality. Patterns of matter that evolve the capacity to measure their environment, no more cosmically significant than any other physical process. Perhaps observation plays a deeper role than we currently understand, a role that future physics will clarify in ways we cannot yet anticipate. Perhaps the question itself is malformed, built on assumptions about the separability of observer, and observed that will eventually be dissolved by a better framework. All of those possibilities remain open. None of them has been closed. But either way, one fact remains. If the final observer in this universe ever closes their eyes for the last time, if the last measurement is made and the last awareness flickers out in the cold dark of a dying cosmos, there will be nobody left to discover what happens next. And that question, what happens to reality when there is nothing left to observe it, may be the only question in the history of conscious thought that can never, even in principle, be answered. Because the answer requires an observer, and the observer will be gone.